Okay, so this is the long-awaited session for public key encryption, public key cryptography. So I've tried to recover the session that I gave uh, for the Monday class, but could not, for some reason, none of the recordings, either locally or on Microsoft Teams, for some reason doesn't do not have any volume. So there's no audio. So uh, let me just check if I can go forward or back on this, because I'm trying to do this in a particular way. Let me see. Uh, Forward. Nope. 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 Uh, that doesn't work as well as I thought. Okay, so I thought I could do it with a slightly different setup. Oops, sorry. So I'm going to do it the typical way, which is kind of sad, but that's how it is. So we're going to talk about public key cryptography. So we'll build up the concept of cryptography starting from the original form. Uh, Mostly, cryptography has been associated with the assumption that you're trying to send a message. There's a sender and a receiver, and the channel in which the message is being delivered is unsafe. It's hostile in some respects. So usually during wartime, so that's why you'll see that the first cryptography, uh, the initial cryptography systems we have for discussion will be based on uh, wars. So Julius Caesar, well known as a general, made use of encrypted messages that they would send from Caesar to people on the field, and they could receive messages back. And if the message gets intercepted, someone intercepts the messenger, the message falls into their hands, they wouldn't be able to interpret it. So they could deliver commands without the commands being uh, prior determined by the opponent. So some amount of strategy can be in place. With additional systems, of course, if the message doesn't get received, you have to have backup, you have to have contingency plans. But the main idea is that messages don't fall into the wrong hands. So we start with the Caesar cipher. So the basic idea is just using modulo arithmetic. You have typically a one-to-one map. So for every letter in the message, you map it to a different letter. So the letter in the encrypted message should correspond to only one other, should be decodable into a single letter. So it requires invertible functions. So replace all the letters of the English alphabet using numbers with A as 0 and then Z as 25. So, they're elements of Z26. And then the encryption scheme is just a one-to-one function, one-to-one and onto function from Z26 to Z26, which is, in this case, a simple shift cipher. So you move the number, basically go along the alphabet by a fixed amount, P. So if P is, so here, we do the conversion from the letters to the numbers. So whichever letter of the alphabet it is, you subtract 1. And then a shift cipher, here in this case, when you shift it by 3 forward, so M goes to N, O, P, E goes to E, F, G, H, T goes to T, U, V, W, and so on and so forth, to get this encoded message. Now, the thing is, if you don't know what the shift is, you won't know how to shift back. You can't figure it out because there's only 20. Well, I guess if the message isn't readable, 0 is not an option. You only really have an option from 1 to 25, and any number outside of Z26 just get the modulo 26. So the remainder modulo 26. And then you can just, so basically, if you had enough time, you could do all the shifts and then figure out which of the messages, which of the prescribed messages could have generated this. So in that case, you're already decrypting it without knowing what the parameter is, what the key is. In this case, the shift cipher requires the key P. So that's easy to decrypt. And that is usually an aspect of the decryption process. It's not impossible to decrypt it. It just takes a large amount of time because the timeliness of the message is important. So it's possible that the message gets intercepted, you recognize that it's a shift cipher, and you start decoding the message by determining which of the parameters 1 to 25, by how much does it get shifted. And you can determine all of the possible encoded messages that generate the encoded message. But it takes it takes a lot of time. For this one, shouldn't take that long because there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 letters, and you don't really need to convert all of them. You can, if you know where the words split, you can just choose, say, the first four, and then decrypt, quote unquote, shift back to figure out what the possible encrypted messages are. And then once you find out that shifting by 3 gives you meat, you try that for the rest of the message, assuming that you have a fixed shift. So as indicated, you can decrypt it by shifting it backward. So that's why we need an invertible function to do the encryption, because the inverse function is the decryption, so that you can get the original message. So when it's if it's properly received by the recipient, who knows what the shift key is, they can readily decrypt the message. So there is that aspect of for this type of encryption, the receiver and the sender have to both know what the shift key is, what the parameter P is, so that it can be decrypted in a timely fashion. Because again, the timeliness of the message is what's important. So we've been referring to P as the key. Usually that's the parameters that are involved in the encryption and or decryption are called keys. So in this case, P is both the encryption and the decryption key. Okay, so you have an example here. You have the message stop global warming with key 11 gives you the encrypted message given here. The encrypted message here, so we won't see this very well because of the weird shift, because I'm trying to write on the thing, so you can actually not see it. So just refer to that. It's LEWLYPLUJL space PZ space H space NYLHA space ALHJOLY is the encrypted message. If it was encoded by shifting forward by 7, the original message is experienced as a great teacher. Now, in terms of cryptography, of cryptanalysis, so there's two actually aspects of codes and the messaging using codes. One is cryptography, the system in which the codes are generated to generate the encrypted message with the intention of being able to be decrypted in a timely fashion. And then there's cryptanalysis. If you are code breaking, if you have received an encoded message and you have some idea of how the how the encrypted message was encoded, then you can perform cryptanalysis. So in this case, the encrypted message has a single letter H, and there are only two words in English that are a single letter, either A or I. So you can actually easily, if you know that it's a shift cipher, determine which of those two gives you the original message. So usually for these types of things, you don't actually have spaces for one, or you might put the space as part of the alphabet. So instead of all the letters from A to Z, you have A to Z and a space, and then you shift. You use Z27 instead of Z26. So this is like the barest bones idea, and for most part, the simplest way to do this encoding decoding process, where encryption is straightforward, decryption is straightforward, usually involves using modulo arithmetic. That's why you often see it this way. So uh, an enhancement of the Caesar cipher is to use an affine cipher. So instead of just one key, you have two keys. So in this case, the keys are A and B. So uh, instead of just shifting it forward, you can multiply the original number by a number A, where A and 26 are relatively prime, so it can't be even, and it can't be divisible by 23. Sorry, by 13, not 23. For any A that satisfies that, not even, not divisible by 13, you can get a slightly more complicated version of the Caesar cipher, which is just by affine transformation. Again, what's required here is that this function is one-to-one and onto. It's a one-to-one correspondence, so that every letter gets mapped to a unique letter. So because you need to invert the function. The encryption function is inverted to generate the decryption function. So you apply a function to a message, you apply the decryption function to the result, you get the original message back. And it has to not encourage collisions. You can't have any ambiguity if you want it to be in a timely fashion. So K, affine encoded, goes to V by the keys 7-3. So both of them are keys in this case. A and B are both keys. They're encryption and decryption key. To decode it, you have to find out from the parameters A and B corresponding parameters for the decryption message. Now note, the encryption message earlier, where you shift forward by P, looks like the decryption function. It looks like you're shifting forward by negative P. So you're just changing the parameter. Technically, you can do the same by shifting forward by 26 minus P. But the encryption and decryption functions uh, are basically the same function. You're using the same mechanism for the function. So in this case, we'll also show that if you have an affine cipher, you can also decode it by using an affine cipher scheme. It will look like this. It will look like A times P plus P modulo 26. It's just determining what replaces A, what replaces B. So what do the two keys become? You have the inverse of A. So that is this is the number such that A bar is equal to 1, well, is congruent to 1 modulo 26. So it's the inverse of A modulo 26. So you need that because you need to solve this. So if you start with the encrypted messages C, you want to solve for A and B. You want to solve for X, and you want to find out what the parameters are. This is actually going to be, so here is the encoded character. You multiply it by A bar, and then you add negative A bar B. That gives you the original message. So the decryption looks like an encryption function where the parameters are A bar B. Well, negative A R B, sorry. And it looks exactly like an encryption function. You just need to determine what A bar and B are. And if you don't know what A and B are, then it now requires a lot more work. Essentially, you're trying to multiply by what are your options. It can't be 0, it can't be 2, it can't be 13. So you have 23 options. 23 options for A. Oh, sorry, can't be even. So you split that by, you're down to 13 minus 1, 12. So there are 12 options for A, and there are 25 options for B. Maybe 26, it can be 0. But this can't be 0. If it's 1, then this cannot be 0. then B cannot be 0. If A is 1, B cannot be 0. Otherwise, it's going to not be an actual encryption. It'll be the original message. It's the identity function, technically. So there's something like 25 times 12 minus 1. You have 599 possible combinations. And that's a lot more than just 25. So again, the encryption and the decryption functions look the same. They're basically applying the same mechanism in this case. So recovering plain text from ciphertext without knowledge or the encryption method or the key is cryptanalysis. So typically, it's a lot harder to do the cryptanalysis if you don't know what the encryption method is. Because unlike what we're doing here, where basically there is a straightforward map. For every character of the alphabet, there is only one character of the alphabet matching that. If there is a single map of that form, then that method means that you can do cryptanalysis relatively quickly. Every time you see a particular character, it will mean the same character in the plain text, in the original message. If a ciphertext, if you're using something like an affine cipher where every character in the alphabet is mapped to only one character in the alphabet, then once you've found out what character matches A, for example, every time you see an A in the ciphertext, it goes, all of those A's will have come from the same letter in the plain text. So that makes this relatively simple. If you have a computer, you only have 599 options, technically, for, if you already know that it's using an affine cipher. Now, typically, for real world codes, it's a lot more complicated, but that's the basic field in which this particular field is in. It's a particular range in which this field is in. So for English messages encoded by shift cipher with an unknown key, use a relative frequency of occurrence of letters. So if you know where the words are broken, you can determine it from the frequency of the words. There are only two one-letter words in English. There are very few two-letter words of as, am, in, of, on, in, so on and so forth. Two. So there's uh, only so much, and you can attack it from that level. So that's actually beyond the beyond the mathematics of it and into the linguistics of it. If you know that the message is in English, it's encrypted in this form, and then you can find out from there if you have code breaks. So that's why these types of things appear as puzzles. So if you've done that type of code breaking puzzle, that's usually what's engaged in that. And real life codes are much more complicated than that. So E is 13%, T is 9%, A, O are both 8%, I and S are all 7%, and HR is 6%. Now, if your message involves a lot of proper nouns, that might be skewed a little. Or especially if you're using a different language, then the frequencies are different. You have different words of particular lengths if you know the lengths of the words in the message. So here's an example of an encoded message where, in this case, the spaces are still there. So this is shift encoded from the early bird gets the worm. So that's just shift encoding. And you can figure that out from, say, the ZNK is the same here. So one of the most common three-letter words is the. You might want to start attacking it that way. If you know that it's a shift encryption, knowing that there's a gap of 6 between all of these letters encourages you to try to use a shift cipher. Of course, if that doesn't work, then you'll try to do a one-to-one map, assuming that it's at worst an affine cipher. So one way to make it more complicated is instead of doing a one-to-one map, you can get it per block. So shift and affine ciphers are character or monoalphabetic ciphers, which are subject to cryptanalysis by frequency. So not very good if sensitive information needs to get through without being decoded. So if your concern is that someone is going to try to determine, trying to intercept this message and determine its contents, then you might want to do something more complicated. So a block cipher, in this case, instead of individually, having a one-to-one map between the characters, you can have maps with blocks. Okay, so a transposition cipher splits the message into blocks. So this is another simple one that's block based. So you put all the characters together, leave out the spaces usually, unless the spaces are part of your alphabet, and then you can do a permutation. So a block of size M can be rearranged. So this is the simplest one that's block oriented. You get them in blocks of M size, and you usually pad the end of the message with spaces or something else, and then you do a permutation. So in this case, it requires a block, but it's still a fixed method. So it's very simple to implement. Just do the same thing for every block. Uh, Permutations are one-to-one maps by nature. So you can undo it by getting the inverse permutation. So whatever process you did to move everything around, you undo it by reversing that process. So that's a little more complicated in detail than it sounds, but that's generally what's going on. So here, if you're using 4 blocks, you can put the first to the third position, the second in the first position, the third in the fourth position, and the fourth in the second. The inverse would be inverse 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3. So again, the process of encryption is a permutation, the process of decryption is a permutation. They're the same type. So pirate attack, which is 12 letters, you can encrypt it as so for the first block, PIRA, the first character goes to the third position, the second character goes to the first position, the third character goes to the fourth position, and the fourth character goes to the second position. So now you see why it's IAPR. So this also indicates that it is a lot easier to decode it if you know how it was decoded. If you're only given this and you weren't told that it was a block cipher, you might try to attack it using a shift cipher or an affine cipher, and it won't work here because it was not encoded that way. So that's why it's actually kind of important to know, to at least have an idea of what encryption scheme is used before you even try to attack it. Because if you start with the assumption that it's using a shift or an affine cipher and it's not, it's done by this permutation block cipher, then you're not likely to get anywhere. You might even get the wrong message in that case. The encoded message SWUETRAEOEHS is encrypted from use water host. So the decryption is first letter goes to the second place. So second is S. Second letter goes to the fourth place, W. Third letter goes to the first place, U. And fourth letter goes to the third. So use W is the first block. And then you can do the same for the 2 other blocks. To get the original message, use water hose. Okay, so it tells you that encryption can be done in a number of ways. So this one doesn't include the use of uh, a shift, but you can actually do that. You can, since all of the functions are one-to-one, you can compound. You can get a cipher scheme that is compounded from, first you do a shift cipher, and then you do a block cipher. Of course, the more complicated it becomes, the more important that the recipient of the message is aware of what the sequence is. So in this case, if you do a shift cipher followed by a block cipher, to undo it, you have to undo the block cipher and then undo the shift cipher. And the recipient should know how to do that, because otherwise the message doesn't get received and the whole encryption process is pointless, because the whole point is to be able to send a message from the sender to the receiver. If the message is not received, then the system fails. So that's why it's important that if you have an encryption scheme, the decryption scheme should be known. So in this case, if you're using any of these, you have to agree ahead of time what type of scheme you're going to use. So you can't have that information along with the message, because if someone intercepts it and finds out here's the encrypted message and the encryption scheme was done this way, then it's kind of pointless because it will be decrypted. So the method and the keys involved in the methods of encryption should be agreed upon ahead of time. So in that case, it uses what are referred to as private keys, because that is agreed upon and is not known. It doesn't get intercepted. It doesn't get. It's not possible to, if you're only aware of the message. It's not possible to determine those bits of information from the message itself. So to generalize, a crypto system, a system of encoding messages to be received, involves P, all of the strings that can be encoded; C, all of the encoded strings, so the ciphertext strings, everything that you can get from it. So it's not necessary that the original message, uh, P and C do not need to be the same, although in the examples that we're going to see here, they're all the same. One of the Okay, so I'll finish this and I'll give some context, because I mentioned that most of these coding systems came about from wars. So there's a lot of applications of codes to wars. So we already saw Caesar mentioned before, and that was one of the innovations that he had, or at least he popularized, which was to use encrypted messages to send commands to the field, so that the opponent doesn't get tipped ahead of time what the commands are, if even if the message gets intercepted. So note that P and C don't necessarily have to be the same space. It could be numbers, so letters to numbers, numbers to letters, letters to sounds, or something to that effect. If you're thinking smoke signals, for example, or semaphores, or Morse code, or things like that. It's not necessarily that the ciphertext strings, quote unquote, are actual strings, but you know, it allows that system. K is the set of possible keys. E is the set of encryption functions. So usually determined by the key combinations. So for a particular set of keys, you use this particular encryption function. Often, as we've seen before, these functions are parameterized. So you just plug in the keys to get the function. Same for the decryption functions, which are the inverses of the encryption functions. So given a key, K in K, so that's possibly a single parameter or multiple parameters. So it could be a tuple. E of K in the set E is the encryption function associated with the key. And dk, which should be the inverse function of ek, is the decryption function. So the shift cipher cryptosystem has the plaintext and ciphertext strings in the same space, with the set of strings with the alphabet say 26. So assuming that you're just working with the numbers in this case, the set of keys is just what shift are you using. Technically, you're not using 0, but it's possible. And this is your set of encryption functions. This is your set of decryption functions. So I'll elaborate a bit here since it's not given. So uh, obviously, when there is some sort of battle scenario going on, if you want to enact a particular strategy with people that are remotely in the field. So whether or not this is physical, like during the time of Caesar, where they would need people on horseback, for example, that can run faster to deliver a message, or even if you're just using in the modern times, if you're using some sort of remote communication. In that case, you have to have a channel that I guess has a minimum amount of security. Probably another channel if if people are going to be prolonged outside. You might want to update your keys. If you're using private keys, you might want to use a secure channel, which often will be remote as well. Uh, so you're using remote communication technology, whether not walkie-talkie uh, or any sort of telephony or broadcast. Well, technically, telephony is better because that's one-to-one. Broadcast is possible if you're assuming that that the keys are private enough that it won't interfere with the security of your message system. Mm, and usually, you don't really give a bulk amount of messages, because if something happens that you need to change your strategy, you need to be able to adapt quickly. So usually, I think the usual timeline is daily. So in particular, there is a confluence of events that happened in World War II. So if you had watched, or you are aware, if you had watched the movie in The Imitation Game, or had read about the main character focused, who's who the imitation game focuses on, Alan Turing. Alan Turing is known to be the father of general computing, because in the process of, so he was brought in to be a code breaker. The codes that they were breaking were German codes. So I think what would happen is they would be able to intercept the German codes, whether or not it was broadcast, or they would intercept it by tapping into the channel in which the messages are sent at the start of the day, and they would spend all day trying to decode it. Now, if it's something like the system that we saw, it shouldn't be too difficult, but it's much more difficult. So, in the European theater of World War II, which is when Turing was brought in uh, to break codes. So the Bletchley Park group, they would spend all day, and then once nightfall happens, it's no longer useful, because they would change the codes, they would change the keys, and so on and so forth. So the message system being used at the time by the Germans was called Enigma. So Enigma actually does do something like the cipher scheme. It is a cipher scheme, except it's much more complicated. So what would happen is, there would be they would use a specialized typewriter type device, where you would it would have the alphabet, and then you'd press a key, and then a key corresponding to a letter, and then a letter would pop back out. Now, the machine itself does the encryption. Now, how does it do the encryption? It's pretty much straightforward. Every character gets translated, except that, so it's not a block cipher, except that cipher is sufficiently sophisticated. So the machine looks like this. There are three disks that you preset at the start of the message. So you need to know so that's part of the keys. The key involves knowing what the original setting of the three disks are at the start of the message. And then every time you press a key, there's a mechanism in the machine, in the Enigma machine, that changes the arrangement of the disks. So I don't know if it's dependent on what key you press, or if it's just press a key, it does something in particular. So uh, it's not the the cipher scheme, even though it's mono-alphabetic, is not fixed per character. In addition, I think the thing that determines how the disks move is, at the back of the machine there are, think, audio jacks. So there are jacks in which wires are connected. So they're paired up. in a particular way. So I don't remember how many there are. I think there's something in between a dozen to 2 dozen, I think, holes. So you pair them up. So the number of holes taken to is the number of possible ways in which that can be wired. So that's also preset at the start. And those determine the motions. So it's the key space is fairly high. The encryption functions sort of change per you there are parameters that are set by the disks that determine what the a particular character is mapped to, and then the ways that uh, the the jacks connected are paired up determine what happens to the disks. So unless you know all of the starting, so that becomes your key space, how the jacks are paired up, how the plugs are paired up, and how the disks start out, you won't be able to generate the same message. So you're generating a message. There is a decryption method. I think you just uh, from the initial setting, you can figure out what the disk arrangement and the jack setup should be so that you can decrypt the message. So it's invertible in that sense, but you have to determine the key, the equivalent decryption key, so that you can decrypt the message properly. So it is an encryption decryption device, and it's sufficiently complicated. I think at that point in time in the war, they'd already gotten a machine, so they know that it's there, but it doesn't tell you how to set it up. And that's actually kind of the important part. Even if you know what the method is, even if you have the mechanism for it, if you don't know what the keys are, then you don't know how to solve it. Now, the thing is, the tactic they used was mostly brute force. That's why it would spend the whole day. So they would employ what would have been called computers at that time, noting that there weren't actual computers then. Computers are a job title. So those would be people. Those would be math people, not necessarily math people, I guess. People that would do the math to try to decrypt the message from sun up to sundown, usually failing. And if they do succeed in finding out, they'll only be able to get it after they've decrypted the message. So what Turing proposed was a way to implement that automatically. That's basically the arrangement for that basically was the foundation of what he used for general computation, for his general computing machines that he's known to devise for, as the father of general computing. So the first machines that they used were used to break the Enigma code that was used by the Germans. So um, that's basically doing the automatic computing for that, and being able to speed it up is the important part. So uh, the mechanism that's involved in that, you get to see a replication of that in the imitation game movie, and it's pretty complicated. They would set it up, it would try to do something, it would spit out something, because the computer would be sophisticated enough to know what the decryption would, if the decryption makes any sense. What it would do is it would take a message, it would perform a decryption, spit it out, perform a different decryption, spit it out, perform a different decryption until an actual message comes out. So it's not sophisticated enough to tell you that this is the key. It's more of, here are the possible, decrypted messages. If any of these make sense to you, then that's probably it, with high probability that is the original message. So the development of the computer as a device uh, stems mostly from that, from code breaking, from cryptanalysis, because the brute force nature of cryptanalysis really requires some way of speeding up the computation. So if you can do it automatically and then perform the action that's required, then you can go through, false results faster. So, and as an aside, the word computer is also something that was used not just in World War II for the people that were doing the coding, but also in World War One. But in that case, it wasn't for code breaking. So this is known from J.H. Hardy. J.H. Hardy, uh, one of the premier mathematicians of the time. He's in, like Turing. Hardy was also in England, and what computers were used, so people that did computations, were used during that war is to determine um, artillery trajectories. So think what your phone does when you do Angry Birds. They were the ones that were computing that. But of course, not like Angry Birds. You'd have to consider real life, factors like if there's wind, mostly if there's wind, and whatever specific factors are involved in the trajectories of mortar shells. So whether or not you can increase or decrease the amount of gunpowder so that you have more or less thrust is the same as whether or not you're pulling the slingshot further back or less. And then of course what angle you set for the trajectory, the initial trajectory of your projectile. So a lot of mathematics has been used in war, and that's actually kind of uh, Hardy mentioned this in his treatise, Mathematician's Lament. Oh, sorry, A Mathematician's Apology, because uh, he saw that other mathematicians from Trinity College, where he was tenured, were invested in the war effort, and he said that I have to apologize. My field of mathematics, which is number theory, the field in which this comes from, have no practical applications. Little did he know that in decades, number theory would be used specifically for codes and code breaking. So yes, there are practical applications. His message did not, age well. It aged as well as in between two wars. Anyways, so that is my aside on history of cryptography, cryptanalysis, and computing. Okay, so let's get to the bulk of what we need to talk about. We want to talk about a public key encryption system. So in this case, there are some keys, not all keys, that are publicly known. And the encryption scheme itself is known. So there is one key that is hidden. And that one key versus the two keys that are known and the system known makes the decryption of this particular scheme uh, take long enough. So it is not timely to try to decode it, even though the only bit of information you don't know is a single number. So even if you are aware of what scheme is used, so in particular this RSA cryptosystem, so you know what the system is, uh, and you actually know some of the keys. So there are three keys that are used: N, E, and D. You know N and E. So you're actually given public keys. There is one key that is held private, and that single key is the linchpin of the security of the system. So private key cryptosystems are dependent on a knowledge of a privately held key for encryption. So this is all of the things that we've discussed before are private key cryptosystems, because if you knew the keys, then you would easily the decode the message, decode the ciphertext. So modern private key encrypted systems are much more sophisticated, such as the AES. So AES, I think, is the usual standard used if you're using some sort of compression. So any sort of encrypted zip files use AES. I think the current standard is AES 256 because the older systems are no longer considered secure. So which requires secure communication keys to be used. So in that case, usually when you encode something into an encrypted zip file, there is a password that's used that is your private key. So the only way to decrypt it is to know what that private key is. Um, I think uh, I think as of maybe last decade, one AES 128 is no longer considered that secure. So I think they upped it to 256. The number that's usually associated is a number of bits. I'm not 100% sure how AES works, but it's dependent on doing the encryption based on the private key and a number of bits. That could be block size or something. I'm not 100% sure. So new keys have to be generated per message and stored securely. So that's usually what happens during wartime. You have an agreed set of keys, and you have to know what keys are used for a particular message. Um, Strangely enough, I'll mention this now. This is the reason why one of the best selling books of all time is a book that just lists all the numbers, all the digits of pi. They're usually used as private keys. So you have a certain number of digits. So you have multiple pages. So usually what would happen is you would agree upon a certain number of digits on a particular page, on a particular line, for a particular day. So that becomes your private key. So you don't need to mention what it is. You just need to have a copy of the book and that, the information of what page, what line, how long, and where does it start. So that becomes your private key because there is a theory of information based on numbers that the randomization only occurs if you're looking at irrational numbers. That's why you're using pi or e or something like that. Because repeating decimals are not random. There's a set pattern. So there is a connection in I forget which particular branch of information theory that uh, connects irrational numbers with randomness. So that's one of the ways in which a random key is generated. Okay, so public key cryptosystems, everyone can have a publicly known encryption key. So everyone that uses the system has a publicly known encryption key, and the decryption keys are secret. So in that case, N, E, and D. E is the encryption. E is one of the encryption keys. N is part of that computation. D is the decryption key. It actually also uses D and N for the decryption, but only D is not known. So D is secret. And only the intended recipient of the message can decrypt it, as knowledge of the encryption key does not let someone recover the plain text without an extraordinary amount of work. So that's the crucial um, innovation of the public key cryptosystems. Whereas before, if it's a private key, if you know the system and at least one of the keys, it makes it easier to figure out what the original message was. In public key cryptosystems, you're given, I'm using this cryptosystem. Here are my public keys. If I send a message to someone, that person can determine the private key to decrypt it. And no one else in the conversation, no one else outside the conversation can figure out what D is. That's the crucial part. Well, as it says, without an extraordinary amount of work. So this is another way of saying in a timely fashion. So I'll say this, I think I mentioned this multiple times. RSA cryptosystem and such public key cryptosystems give you an idea of how e-commerce works. Because for e-commerce, you're basically trying to send information that's sensitive to bank information, credit card information, and you want it to be verified by the merchant. If you're buying from a merchant, they should be able to verify it, and you should be able to transact without anyone else getting your information. So first, that person must be trusted, so that you don't worry about whether or not that person gets that private information. they will handle it in a reasonable fashion. So that's outside the realm of the actual crypto system, but that's assumed. And uh, the information that's available, so usually it's through a broadcast channel, the internet. It's usually through a broadcast channel, whether or not you're using secure communication or not. It only adds a level to it. The information there is encrypted and cannot be decrypted by anyone who is not in the information. So malicious uh, eavesdropper, I think, is usually the description. An eavesdropper cannot determine from your public key and from the encrypted message what the original message is without doing an extraordinary amount of work. So just that single bit of information, well, I shouldn't say single bit because that implies that it's either a 0 or 1. That single piece of information, the decryption key, is sufficient for the recipient to be able to um, use the information in a timely fashion, and insufficient makes it insufficient for anyone else to try to figure out what the original message is. So the last bit that's here that's not written, in the RSA crypto system, each individual has an encryption key, n is equal to p times q. So the parameters you're actually using are p and q. From there you get n is their product. You have another key e, and p and q are large primes. So n is a number with 4 factors: 1 itself, p and q. And by the time that this was written in the book, I think it was 2011, 2012, 200 digits. So you have to be able to generate 200 digit primes quickly. So that actually kind of implies that you have to have a system where you can generate these primes in a rapid fashion. So that's also beyond the system itself, and that's why one of the things that's explored usually in computational systems is how can you determine if a number is prime or not, especially if it's 200 digits long. So that's actually something that takes a lot of time to do and is important for this effort. And more importantly, the other key E is relatively prime to the product P minus 1 times Q minus 1. So that's curious. And that's actually the mathematics involved makes this particular property important. Now, the idea is that if you have n, it takes a long amount of time to get the prime factors p and q. If you know what the prime factors are, you can determine p minus 1 and q minus 1. So, how does the encryption method work? So, RSA encryption says plain text English message translate each letter to a 2-digit number. So, again, translate each letter to 2 digits in Z26, and then you get those sets of digits together. So you use a block cipher to them. So you have blocks of 2n digits where you're using n letters. So this is the simplest description of this. Of course, in actual use on, say, e-commerce, you're not actually sending a plain text English message. It's usually already in number form, but that shouldn't matter because you're just looking at a particular number. So uh, divided into blocks of 2n digits where the 2n digit number is less than n. So n is one of the parameters. So if n is the product of 200 digit primes, it's probably 400 digits long. So this is probably 200. Capital N is 200, thereabouts. Maybe less if necessary. So the last block may be padded with zeros at the end. So you do the shifting and then you pad the last block with zeros if need be. And then you get a plain text message, which is a bunch of blocks. So K blocks, each of which is of from 0 to 252525, so on and so forth, 400 digits. Okay, so for each of those blocks, you're converting each of those blocks to a cipher block, which is performed just by this. So this is the straightforward action. Here's the first key, there's a second key. Now, mi to the e mod n. Now, okay, you might wonder, oh wow, e, you're raising a number to e. How do you do that? So usually the process there is you get the binary form of e, and then you get the squares of mi. So you get mi squared, mi to the fourth, mi to the eighth, all the way to mi to the 2 to the k, where k is the number of digits in the binary form of e. And then you just multiply these together. Now, the thing is, whenever you do a multiplication, whenever you're performing a multiplication and then you get modulo n, for every sub multiplication, so you can think of this as mi times mi times mi e times, which could be something like hundreds of millions of times. You can actually perform this multiplication, so you get this first pair, and then you can immediately get modulo n. So what you want to do is you want to minimize the number of multiplications that you do. So the minimal way to do it is you get all of these squares, and then you multiply together the powers that correspond to the one digit, the one digits of the binary form of e. So that should get you mi to the e. And then for every multiplication that you do, so like to get the square, you're multiplying mi to mi, get the modulo n. So every multiplication has to be assumed to be a modulo multiplication, which is basically two processes. So depending on what k is, you'll only break down the binary form of e once when you start, so you don't need to do it every time you do a block. So you have an action doing that, which is just divide by 2, divide by 2, divide by 2. If the number is odd, you get a 1 digit. If the number is even, you get a 0 digit. Just keep dividing by 2, removing remainders, and then you get the binary form. So that's one set of divisions. If it's assuming that it's about 200 digits as well, that means that it's every 3 digits is 10 to the 3 is 2 to the 10. So divide that by 3. Let's say you get 198. That's 66 times 10. So 660. So say about 660, 600, let's say around 700 divisions for that to get the binary form. And then you do these as 600 multiplications as well. So that's 1,000, let's say 700, 1,400. That's 2,000 computations, which can be done on a computer relatively quickly because that's 2,000 floating point operations. To give you an idea of how quickly that can be done, when your computer's CPU is at the gigahertz level, that's floating point operations per second. Giga there is 100 million. Sorry. Mega is a million, giga is a billion. So a billion operations per second. And each of these is just 2,000. So it's not that difficult for a modern computer to do, despite the numbers that are involved. So uh, so that's the basic operation here. So even though if you're doing this in person, this is going to be difficult, on a computer that's not too difficult to do. So you can imagine that if we had a paper test for this portion, I would have actually put in one portion where you're either doing an encryption or decryption. So imagine that this would be one of the questions you do. I mean, I think you can see the portion on the book on this. It's straightforward, relatively. Okay, so here's an example. So n is 43 times 59. 13 is relatively prime to 42 and 58. And their product. So to encrypt the word stop, so you have to take it in pairs of 2s, because this is slightly larger than 2525. So you can only get 2 letters. So you encrypt each pair of letters separately. So you get this block and this block. And then you raise this to 13 modulo 2537. So 13 is 8 plus 4 plus 0 plus 1. So you'd have to get the original message, 1819. You have to get its square, which you won't use. And then you have to get the square of that, which you will use. And then you get the square of that. So 1, 2, 3. 6 operations. 4 operations here. 3 operations. And then a multiplication and then a multiplication. So that's 5 operations to get the corresponding block for S and T. So 5 more computations for 1415. That gives you 2181. 2081. And then for 1415, you use the same operations. You end up with 2182. So the encrypted message would be 2081 2182. So that's it. That's the encryption method. And the decryption will look like that. Now, I'll tell you that the decryption is actually, the decryption key is D, where D is the inverse of E modulo this product. That's why you need it to be relatively prime to P minus 1, Q minus 1, times Q minus 1. Because you need to get its inverse under that modulo. Okay, so since they're relatively prime, that inverse exists and it's unique. So how do you get the inverse? You use what you do is you use Euler's theorem, Euler's algorithm to determine that the GCD of E and this number is 1, and then you reverse it to get the Bezout coefficients. So you'll get S times E plus T times P minus 1, Q minus 1 is equal to 1. So that means SE is equivalent to 1 modulo P minus 1, Q minus 1. And S is D from the Bezout coefficients. So we already know how that's done. So why is that the decryption key? And we know that that's difficult. It's doable if you know what P minus 1 and Q minus 1 are. We already know how Euclid's algorithm works. And no matter how large the numbers are, that's not going to take too long. I think if you're in the hundreds of digits, 200 digits, it's probably not going to be longer than 1,000 computations to go one way, another 1,000 computations to go in reverse, about 2,000 operations. Again, not too difficult to do and doesn't take that much time. So you can determine the decryption key if you know E and P minus 1 times P minus 1 times Q minus 1, which you only know if you know what P and Q are, because if you only have N, it's not easy to find out P and Q. Okay, so you can get the decryption key. Here's the decryption. Basically, it looks like the encryption key, except that the encryption function, except that you've replaced E as the exponent with D as the exponent. So you're using the same mechanism. And we've already seen that mechanism in action. So it's not difficult to imagine that that's doable. Now, why does that work? Why is this the inverse function? So these are equivalent modulo n. So if we started with the encryption, so the encrypted block is mi raised to e. So that gives you ci. Raise that to d, that gives you this. So these are the same modulo n. Okay. So in that case, you can get mi e times to e times d. Now, according to our definition of the decryption key, de is equivalent to 1 modulo p minus 1 q minus 1. So it's equal to 1 plus a multiple of this modulo n. Now, okay, that's something, but how do we know that this gives us the original message mi? Well, to prove that, we need a couple of things that we already discussed prior. One is uh, it's safe to assume this. Okay, so uh, this is safe to assume in the sense that mi uh, is highly unlikely to be a multiple of p or multiple of q. So it kind of relies on this being the case, that it is not very likely that it's a multiple of p or a multiple of q. Remember that m is about as long as n, and n is the product of p and q. So um, this is kind of something that happens probabilistically. So the likelihood of this not being true is not very high because there's a large number of messages. Uh, there's only so many multiples of p and q that are available. Even if p and q are large, sort of like 400,000. So 10 to the 400,000 is about the size of mi space. So the number of possible messages. The number of multiples of p is about q. The number of multiples of q is about p minus their intersection, which is just n actually. So out of 10 to the 400 possible messages, q plus p of those messages are not going to satisfy both of these conditions. So even if these are 200-digit numbers, 200-digit numbers, so that's roughly something on the order of, say, let's say 10 to the 201. So these are the number of messages that will not satisfy this. This is the total number of messages. You're looking at something like 2 to the 5 times 10 to the 198, which is a really large number, is to 1. So the probability that your message is not going to satisfy this is very, very small. Vanishingly small in this case. So if that happens, then it will break down, but it will break down only for that particular block, which probably will flag something. I think there are some mitigation methods for this, but in this naive implementation, the probability of these not being true is very, very small. So so because that's the case, according to Fermat's little theorem, any number that is relatively prime to p raised to p minus 1 is congruent to 1. If you raise that to if you raise this by q minus 1 times k, you still get 1 because 1 raised to any number is 1. So you get this is equivalent to 1 modulo p. And then you also get that. Okay, so this is what we have here. So CID is congruent to, this is mi to the 1, this is mi to the rest of this. So this is congruent to 1. This is 1 raised to any number is 1. So it's mi times 1 to some power, which is mi. So CID is congruent to mi modulo p. Likewise, Ci to the d is also congruent to mi modulo q. So these are not this. These are not n, by the way. N is the product. Now, we know that whatever this is congruent to mi modulo p. And whatever this is congruent to mi modulo q. According to the Chinese remainder theorem, there is a unique, since p and q are relatively prime, they're both primes, and they're not likely to be multiples of each other. They're not likely to be equal, to be fair. Chinese remainder theorem says that there's a unique answer. So let this be x, this x, there's a unique value x equivalent to some value. You should find a value x congruent to something modulo the product, which is n. So this is congruent to CID. So that is congruent to something. But if it's congruent to MI in both cases, and that's unique for this product, well, it's safe to say that the Chinese remainder theorem also says that this is congruent to this number, Mi, modulo the product. So Ci raised to D modulo N is Mi, which is the original message. So the mechanism here requires Fermat's little theorem. Uh, it uses the way we described E and D, and it uses the Chinese remainder theorem to prove that this decryption function is the inverse function. So that's it. That's the entirety of the encryption decryption scheme. You have as public key N and E. N is a product of two primes that you know, P times Q. And then E is relatively prime to P minus 1 times Q minus 1. Its inverse, modulo P minus 1, Q minus 1, is the decryption key. So this is something that has to be sent ahead, I think. I think that's usually the case. You share the private key. So there is a secure channel in which the private key is given, but everything else is known. So if the recipient knows D, even with the public key that's given, you wouldn't be able to know what the decryption key is unless you can factor N. So the crux of the secretness of D is that you cannot factor a number which is a product of two 200-digit primes in a timely fashion. So here is the decryption from the original one. So the encryption key is 47 times 59, and the encryption exponent is 13. The decryption exponent is 937. So it's a lot larger than 13, but the mechanism should still work the same way. So if you're given a message 0981 0461, you can decode it by segmenting it, raising this to 937. Again, you get the binary form, you get all of the exponents up to, in this case, 512. And then you figure out which ones to multiply. So that minimizes the number of operations. Every operation that involves multiplication is modulo multiplication. So you get the modulo of 2537. So that should get you the computation 704 and 1115. So the original message is 07 04 1115. H E L P. Help. So to recap, to use RSA encryption, generate large primes P and Q. P and Q generates N and the product that you need to determine the second encryption key. You need something that is relatively prime to that, so it can't be even for 1 because this is definitely an even number. It's divisible by 4, since large primes will be odd numbers. So that's an odd number as well. So you can do trial and error for this. You can generate a random number E and then determine the GCD. If it fails, generate another E. So E has to be odd at the very least. So once you do that, you're also in the process halfway through determining the inverse. So parties can send encrypted message MI to a party with the encryption key and by sending the encryption. So this is equals, so which only the recipient can decrypt back. So D has to be something that the recipient knows. So that is usually the the initial message, once you've ascertained that you're both safe, send the decryption key, and then they can decrypt it. So even if the message is done through a public broadcast channel, like the internet, knowing what N and E are, since that's actually available from you. So basically, it's something that you can see is, oh, I see this is the sender. The sender uses this public key, or for this message, is using this public key. So decryption cannot be done without factoring in, which is believed to be a difficult problem. It's what's referred to as a trapdoor problem. It's easy to do one way, but difficult to do in the opposite way. So if you're going in one way, trip, you trip it's easy to go through the trapdoor from below it instead of through the trapdoor from the top. So the trapdoor only opens one way. So that's why it's described as a trapdoor function. Note the sophistication of computers often leads to larger values. I think 200 digits is no longer sufficiently secure. They might have already migrated to 400 digits. So how do you send a private bit of information? So one thing that can be done is this. So you can have what's referred to as a cryptographic protocol. So for two people that have private keys, so they agree to publicly use a prime and a primitive root of the prime. Alice has a private key K1 and Bob has a private key K2. Alice publicly sends Bob A to the K1 mod B, since K1 is Alice's key and K2 is Bob's key. So they can perform this action. So only they know the numbers. You perform that action. So this is another trapdoor function. If you have a number, so as a power of a primitive root, this was referred to as the discrete logarithm. It's not easy to determine the discrete logarithm. So it's not easy to, even if you know A and P, it's not easy to know what the exponent Ki is in this case. So Alice and Bob use the shared key. So now you have a common key that you can use, because no one outside the conversation knows K1 or K2, and now they have a common number. So if you need a communication that requires a shared private key, so this can't be used with RSA encryption in particular. So RSA can be another use for, so this is to be able to generate a private key if you start out with two private keys. So you get a shared private key in this case. So RSA encryption, other than what's described earlier, can actually be used to indicate a signature, to indicate that this message comes from you. So you have a public key that's known. You also know your private key. So what you can do is a sender with uh, encryption key NE and decryption key D sends a decrypted message. So you start with the message and you decrypt it. So you perform the decryption operation. Anyone that receives that can verify that that message comes from you by using your encryption key, because the encryption key is the opposite of the decryption key. So, which can be encrypted, quote unquote, to the original message MICE raised to E modulo N by any recipient who knows the sender's encryption key. So, to verify that it's you, because your key NE is given, they can receive your decrypted message. So you're undoing you're doing an encryption using the decryption key, which can be decrypted by using the encryption key. So it verifies that the message comes from you. So they can read the message, and it verifies that the message has to have come from you. So that's another. This is actually what's used. This is the basic scheme for PGP encryption as a digital signature. So, you can use RSA, the crypto system, to also initiate digital signatures. And that's it. That's the last slide. So that's everything that the book mentions about cryptography, in particular the concept of public key cryptography, because it involves fairly sophisticated mathematics. It involves the use of particular theorems. The reason why those theorems were discussed is because it helps describe why this works. And this is kind of important because it gives you an idea. I don't know if it's exactly this. I don't think that e-commerce is still using something like RSA, but it uses, more sophisticated versions of public key encryption systems. So it also makes, highlights what things you can be sensitive to in terms of what you're trying to deliver. So the goal is always to transmit a message safely from a sender to a receiver. Now, the rest of it has something to do with what what type of channel do you have? Uh, how can you uh, public key encryption allows you to provide more information so that, for example, this digital signatures can be verified, and it also gives you some insight as to how these systems can work and what mathematics are involved, especially the use of trapdoor functions. So that's why they say that if it is possible to get the prime factors of a number relatively quickly, e-commerce will collapse because uh, generating primes and the difficulty in factoring large numbers is usually at the heart of these trapdoor functions and is usually at the root of most encryption systems that are in use that are public key based, including whatever is used for using your credit card online or any sort of digital signage system. They all rely on the intractability of that type of thing. Of course, that's sort of an arms race in the sense that if your computer gets faster and faster, you need to use larger and larger primes. But the it really just makes it so that if you can now get the prime factors of a decently sized number quickly, you just need to increase that, maybe double the number of digits, and it'll be a further goal for most systems. So that's it. This completes the discussion for chapter 4, and hopefully you'll find something useful about this. Thank you for your time. Good luck in whatever adventures in adjacent to mathematics, with mathematics in particular, you'll find yourself in. Hopefully, you'll remember where you can find it. You don't need to remember all the details, just knowing where to start finding it, knowing what terms are used for it. Often gives you at least the initial Google search. Oops, sorry. The initial search string that you need in order to get the information. And it should help jog your memory. Now that you've seen it, you have some ideas, you can, apply these later on without necessarily needing to know all of the details. Okay? So that's it. Thank you for your time. See you when I see you. Stay safe, stay healthy, stay vigilant. I figure anytime you hear this in the near future, we will still be in these types of times. It's always useful to at least be vigilant wherever and whenever you are. Okay, see you when I see